I'd like to welcome Professor Alastair Wilson, who's going to discuss a perennial question, explaining the Big Bang. Again, 30 minutes and 15 minutes for. 15 minutes for questions.
Well, thank you, Francine. Thank you, Joe, and to the Centre for the invitation. So I'm going to talk about the Big Bang and all the different ways we might explain it. I'm a philosopher by training and activity, so these will be kind of philosophical questions. So I won't be going very deep into the physics of any of the different Big Bang theories. The aim is to kind of use the different physical theories as examples of the kinds of possible explanations that we might try to give for the Big Bang. So the Big Bang I'm thinking of as a kind of first cause in the ordinary sense. So it explains all the events in the universe in the sense that you can trace a space-time trajectory, a time-like space-time trajectory back from every event to the Big Bang. So it's a kind of ultimate explainer in that sense. It explains all of the events that come after it. Can we explain it itself? So I'll look at a few different kinds of explanations. I'll look at causal explanations, where we're looking for something that caused the Big Bang, which in turn then causes everything else. But I'll also look at various kinds of non-causal explanations that aren't straightforward kinds of cause and effects explanations. So here's a picture of the Big Bang. Many of you will have seen something like this before. The Big Bang is that kind of bright flash on the far left that gives rise to everything else. So the universe doesn't look quite like our ordinary universe for a short while after the Big Bang. Sooner or later, it starts to look much more like the kind of universe populated by stars and galaxies that we're used to. So the Big Bang is kind of a core part of modern cosmology. It's a core part of the best models we have of the overall shape of space-time of our universe. That is the lambda CDM model. The lambda stands for expansion constant. CDM is cold dark matter. And so our best theories, which are really, really good at modeling lots of features of matter distribution and especially of the cosmic microwave background radiation, this kind of colourful patch with the green on it that's been mapped by satellites, including the Planck satellite. And so we have really quite a lot of confidence in this, in the broad model, and even more confidence in the idea of a Big Bang. Lambda CDM is just one instance of a Big Bang style theory. So in this picture, we have a Big Bang, and that sets off this kind of cascading causal chain where different phases of matter kind of pass by until eventually we get stars, stellar fusion, and the generation of more generations of stars, then planets, and so on. But the Big Bang is key to this story. Without it, we don't get anything else. So, as I've already said, we don't know a lot about the physics of the Big Bang. We don't really know exactly how the Big Bang itself worked. We kind of can tell quite a detailed story from a very, very short time after the Big Bang. But as we go back to the Big Bang itself, as space-time seems to approach a singularity, we face all the problems of understanding gravity in a quantum way, understanding a quantum theory of gravity. Below the time scales and length scales associated with the Planck's constant, we have no good theory to tell us what was going on. So we know that kind of what came out of that extremely high energy, extremely dense, extremely small state, but we don't know exactly what it was prior to those Planck limits. So unless we use a specific theory of quantum gravity that starts to describe what goes on at the Planck energy scale, we can't tell the full story here. And I'm not going to go into the details of any of those theories, so I'm not going to try and tell the full story. But what I want to do is explore the kinds of explanations we could give of how the Big Bang got started. And I'll use some different theories that do stick their neck out a bit and say something about quantum gravity as examples of these sorts of candidate explanations that we might try and offer. So, kind of, as a philosopher, I like to categorize things. One of the biggest divisions in philosophy explanation is between causal and non-causal explanation. I mean, this distinction obviously goes back thousands of years. Aristotle had his 4 causes, kind of only one of which, efficient cause, is really quite like the modern notion of causation, where we have cause and effect. So the modern notion of causation is kind of stereotypically associated with things like rigid impact, so like one billiard ball hitting another billiard ball and the bouncing off. Those sorts of causal processes are actually kind of the exception rather than the rule. Very often there's kind of continual causal process, kind of energy exchange, those sorts of things. But most, I would go so far as to say, of the scientific explanations we give are causal explanations of some kind or other. And when we teach physics, we use causal explanations as kind of the core examples of kind of what we understand about the basic workings of a thing. So when we're talking about why the planets orbit the sun, we give an account in terms of a gravitational force that is directed centrally towards the sun and kind of keeps the objects moving circularly. At least that's kind of what we teach at kind of GCSE and A-level. When it comes to more sophisticated physics, the story gets more complicated. We often find other kinds of explanations, equilibrium explanations, for example, the kinds of which I'll come to later. But a lot of the most basic explanations in any branch of physics and in science more generally are a matter of what causes what. And we investigate these roughly by finding out what we can intervene on and what we can control by intervening on those things. So if you were to kind of get rid of a large amount of the sun's mass, then we would have different orbits. If you were to apply a different voltage to a circuit, then you would get a different current for the same resistance. So different cause leads to different effect. And these are the sorts of explanations that we kind of understand most instinctively, I think. And physics definitely contains some of them. The way I would model these, the way I think kind of a lot of different philosophical theories broadly agree on how we should model these, is as explanation where there's some law or laws of nature that link the cause to the effect. It's no coincidence that when the cause occurs, the effect occurs. There's something, law-like, that links the cause with the effect. Some general principle that says causes like this leads to effects like that. Broadly speaking, we can think of that categories as laws of nature. Not just the fundamental ones, laws of at all levels. These sorts of general principles linking cause and effect. So I'm using these terms in a really quite kind of general and inclusive way. We're just trying to mark a distinction between causal explanation on the one hand and non-causal on the other. So non-causal explanations tend to be explanations of kind of what makes something up, how something kind of gets to be what it is. And perhaps the easiest to think of is the explanation of bulk properties like temperature and pressure of gases and other systems in terms of their underlying molecules and the collective behavior of those molecules. So, a gas gets hotter when its constituent molecules start moving faster, all other things equal. And that kind of increased heat being explained by the increased motion isn't cause and effect in the ordinary sense. It's not that kind of increased motion comes along and bumps into the heat and then increases the heat. Increased heat just is made up of the faster motions of the molecules. So that sort of explanation is not naturally understood as a cause and effect explanation. And there are lots of other examples in and outside physics. I've mentioned equilibrium explanations as kind of why a system is, why a particular state is reached as a kind of example of reaching an equilibrium. But we can also give more kind of theoretical explanations, such as the explanation of the stability of atomic matter in terms of the Pauli exclusion principle, that you can't put all of the electrons in an atom into the same base energy state, so you have to build up orbitals, you have to get, that's where atomic orbitals come from ultimately, this kind of theoretical explanation in terms of the Pauli exclusion principle. But the Pauli exclusion principle there is not acting as a cause. So any explanation involving it is going to have to be a kind of non-causal explanation. And non-causal explanations are philosophically really interesting, much kind of less familiar to us than causal explanations and correspondingly harder to understand. The key to understanding them is often the concept of reduction between one theory and another, where you can explain the effectiveness of one theory in terms of another. Classic example, to kind of stick to the theme, we're explaining the effectiveness here of kind of the chemical table of the elements in terms of the different stable atomic structures. Or you could explain the effectiveness of thermodynamics in terms of statistical mechanics. We might not always have a complete reduction there. We might not be able to completely account for thermodynamics in terms of statistical mechanics, but we can account for a lot of its general features, which give us the confidence that thermodynamic systems really are just complex systems of molecules kind of acting together. So quantum gravity makes that kind of neat division between causal explanations and non-causal explanations a bit more complicated. Because we're used to causal explanations happening over time, where the cause happens first and then there's an effect. Or at the very least, the cause kind of triggers kind of a process that continues. But in several, not all, contemporary theories of quantum gravity, space and time aren't basic. The basic physical ingredients of the world aren't kind of laid out in ordinary space and time the way we take ourselves, matter to be laid out in ordinary space and time. So you think of like what we see in space and time as like kind of waves on the surface of an ocean, and there's lots going on underneath that isn't itself on the surface, that isn't itself in space and time. And we're not very good at thinking about how cause and effect could work in the absence of time. If there's no space and no time, it's unclear how causation, conceived of as happening across time, could exist. So how could there be causation in quantum gravity at all? I think Matt Farr later might return to some related questions. But I think it's possible to think causally, even kind of outside space and time, as we'll see in a minute. Okay, so I've talked about some different kinds of explanations, causal explanations and non-causal explanations. So let's try thinking how we might try to explain the Big Bang causally. Now, there are kind of some big claims out there in the literature. Lawrence Krauss has a book called A Universe from Nothing. And there's a kind of entertaining, kind of quite acerbic exchange in the New York Times where David Albert reviews this book, and there's a kind of back and forth about whether or not this really is getting a universe from nothing. So what Krauss thinks he's doing is getting a universe from nothing because he's getting, or claiming to get, using kind of some, like a package of contemporary theories, matter out of space-time vacuum states. So we start with a space-time vacuum state and we end up with matter. But it's not really much of a nothing the space-time vacuum state. There's kind of a lot going on inside it. We think of space as empty, but in quantum field theory, space is active. Particles popping into existence, disappearing, and there's energy associated with the background state itself. So if we're explaining where matter comes from, if we're explaining where the matter comes from just in terms of an initial vacuum state, we're getting something from something rather than something from nothing. That's the gist of Albert's criticism. I think it's on point. So we can take a step back and ask kind of where did space-time itself arise from? Set aside kind of where matter came from inside space-time, where did that initial space-time itself come from that then can be a home to matter? That's where quantum gravity comes in. That's where I'm not going to give any satisfying answers. But I will talk about how we can think about cause and effect as stretching back kind of prior to a well-developed space and time. The account I gave of what cause and effect is an explanation which is backed up by laws of nature. It's an explanation where there's some general principle which is a law of nature which explains why the cause of that kind gives rise to an effect of that kind. And that didn't make any essential reference to space and time. As long as we kind of separate the idea of a law of nature kind of from the idea of a law of nature that acts over time, we might have laws of nature that explain connections between physical systems, either where those physical systems are outside of space and time as we know them. So just to kind of give a hint of what I mean by this is an example from a paper by Enrique Gomez, it's based in Oxford, whereby the top picture is the kind of well-defined, well-ordered kind of temporal history where all of the records of an earlier time are present at a later time and kind of build up sequentially. And this is the kind of time that we have, kind of in our regions of the universe. But he points to these other sorts of structures where we haven't got what philosophers and logicians call a total ordering. These kinds of cause and effect, these kinds of systems, he's arguing, can still interpret it as cause and effect even though we don't yet have time. We only have time at the top layer, but we still have cause and effect even without an ordinary, well-ordered timeline. So it's kind of hard to disentangle our notion of cause and effect from time, but in these sorts of quantum gravity contexts, people have been trying to do it. So we can keep tracing back, but sooner or later we're going to have to talk about kind of the initial quantum state of the universe, whether that thing had matter in it or not, whether that thing even had space-time in it or not. Where did that come from? That kind of basic kind of initial condition for our theory of quantum gravity, whatever that theory might be. Broadly speaking, there's two options. We can say that that initial quantum state, if we want to explain it, that is, we can say it didn't have an explanation. If we want to give a causal explanation, we've got two basic options. What I'm going to call creation explanations and what I'm going to call recurrence explanations. And then amongst recurrence explanations, we have linear and we have circular. So creation explanations are this kind of familiar idea. There's something external to the universe, typically something supernatural, perhaps divine, a creator. And we heard from Adam about some of the different kind of creation accounts, or kind of mention of them, but I'm going to kind of extrapolate away from it kind of abstract away from all the details of what did the creating, and kind of consider, is it possible to give a genuine explanation in terms of creation of the initial quantum state of the universe? Well, unlike a lot of philosophers of physics, I don't see that that's kind of an illegitimate form of explanation. We should kind of assess those explanations like we assess other explanations. They're not physical explanations, but they could be explanations nonetheless. But I think kind of the challenge, the structural challenge that these sorts of creation explanations face is in explaining where the creator comes from, and in making a case that it's easier to explain where a creator that would create a universe just like this comes from than it is to explain the universe just like this by itself. I think, I'm not going to kind of argue that this can't be done or that it hasn't been done, but the kind of creator that would make a universe just like ours itself apparently kind of is a thing that you can also then go on to ask, well, what explains that? Perhaps there are special reasons why that creator doesn't need explaining. Then the question is, why can't those reasons apply to the universe itself? So there's a kind of challenge. What features does that creator have that exempts it from explanation that the universe couldn't just have itself directly? So I won't say anything more about that sort of explanation and that sort of objection to it. But suppose we just happen to think we had some strong independent reason to think that there is some kind of designer that would create a world just like this. Why would they do that? What is it that our universe optimizes? Some people have suggested that our universe optimizes life, and I'll be talking a bit more about that after the break in terms of fine-tuning. But it's not obvious to me the universe really is optimized for anything much in particular. There doesn't seem to be a maximal amount of life. There's quite a lot of it, but there's also a lot of empty space. There's a lot of barren planets. You'd think it would be possible to make a more highly populated universe if that was really the point. So, perhaps no doubt stories can be told here, but there's a kind of prima facie challenge. If you were, what would you be trying to optimize for, plausibly, that would give you a universe like this? So I'm going to look, probably for most of the rest of the time, at a different kind of explanation, recurrence explanations. And here I'm going to focus as an example on conformal cyclic cosmology, which is been put forward by a local hero, Roger Penrose. So without going into the details of the physics, the idea is that although there look like there are very major differences between the very hot, dense state of the universe at the Big Bang and the very cold, empty state kind of in the distant far future, there's a certain feature, roughly shape and roughly smoothness of shape, which they have in common. And Penrose has this radical idea that these states, the early state of the Big Bang and the far future state where everything's kind of completely smoothed out and emptied out, might actually be one and the same state, one and the same type of state. So this is a picture that Penrose has produced from his amazing hand-drawn slides. And this is the kind of Big Bang here. This is the universe it produces. Eventually it becomes very big and very empty. So big and so empty that there's going to be, in the entire kind of visible universe as it is right now, a region that size on average will have less than one photon in it by the time things have really spread out and emptied out. There will be pretty much nothing at all. And that sort of empty state is very, very kind of smooth, has certain distinctive features which render it linkable via this operation of conformal rescaling, which I won't explain, to a Big Bang. And so this is Penrose's picture. We actually have one universe after another, and the kind of heat death of the universe, it becoming cold and dead, just is the Big Bang of another. And so we have a kind of recurrence explanation of the kind Adam mentioned that the Stoics endorse, whereby you just have kind of continuous cycles and things play out differently in each cycle. And there might even be evidence that kind of crosses these gaps we might be able to spot previous universes in when we're doing astronomy. And Penrose and his collaborators think they might even have found this yet. Most physicists don't think they've found it yet. Most physicists don't think they kind of can or will find it. But it, philosophically speaking, it illustrates a kind of possibility for a recurrence explanation where there could, in principle, be signals between the universes. I've suggested an alternative way of doing this that doesn't have many cycles, that sees the end cold dark state as just the same as the hot dense state, but just in a kind of one cycle loop. So the universe cycles round and around again, and the same things happen again and again and again. It's a kind of a time loop. You still have the same feature of conformal rescaling, but it's now one kind of circular donut rather than a long tube. And this sort of picture, I think, is especially interesting if you combine it with the many worlds interpretation of quantum mechanics, because then in that one cycling round of the universe would still live all of the different possibilities. So you'd get all the different possibilities kind of playing out in parallel, and then those very same possibilities would all play out in parallel again, and so on forever. And so the explanation for the Big Bang would be in terms of kind of that whole system having played out, come round to the starting point and starting again. So we'd have a causal chain that, so to speak, kind of goes round forever and contains all possible histories within it. The kind of downside of that is that you lose any possibility of any signals coming through the loop, because now kind of all possible universes happen and have to kind of recombine. So that's going to wash out any possible signals. So we're not going to get any direct evidence for a view like this in the way Penrose is hoping to get a direct evidence for his view. This picture would be less falsifiable. But falsifiability is a whole can of worms I'm not going to go into. A lot of the theories I think we should be at least exploring are not directly falsifiable. So I'm almost out of time. There are various kinds of non-causal explanations that I'll just talk about, I'll just kind of mention rather than talking about in detail. I've focused on causal explanations for the Big Bang, finding something that can be the cause where the Big Bang is the effect. And that thing could be a creator, that thing could be a previous universe, it could be the universe itself at its own end. But if we look away from causal explanations to different sorts of explanations, there are a few other kinds of explanations we can explore for the Big Bang. Some of them might seem unsatisfying, but I think it's worth mentioning. A grounding explanation says kind of what the Big Bang is made of, roughly. What the Big Bang is based in, or what constitutes it. And some philosophical views, for example, idealism, that says everything is mind, ultimately, and the kind of matter is secondary to mind, have an answer here. They say, well, the Big Bang is made of the collective activity of minds. That's why we have a Big Bang, because the minds are collectively acting in a certain way. You might not think that's the kind of right sort of explanation, but it's not obviously a causal explanation, and it's something we can at least, I think, conceive. So I'll skip this. Here's a kind of more physics-based sort of grounding explanation. One mechanism for saying kind of where space-time comes from is that it is made of entanglement of systems that aren't themselves in space and time. One version of this has been put forward by Sean Carroll and collaborators. And this would be a matter of explaining kind of what made up the space-time state that was the Big Bang, in terms of something that wasn't itself in space and time. But this kind of non-causal explanation is like the causal explanations, some of them we discussed, in that they just kind of push the explanation back one stage. Well, where did that like complex entanglement state come from? Again, we have a question that needs answering, or looks like it needs answering. One way of trying to explain why we have the universe we do is that we say, well, we have all the universes in a given class. And our universe is in that class, so it's no surprise that we have the universe that we do. David Lewis gave a view like this in a kind of purely philosophical setting. But you can probably guess where I'm going to go next. These sorts of explanations don't push the bump in the carpet very far. We can still ask, well, why do all of those universes exist? And you might think that if it's hard enough to explain why one exists, it's even harder to explain why a whole set exists. Or you might think it's easier to explain why the whole set exists, because you don't need the arbitrary thing of picking out one in particular and leaving aside the others, so you have less arbitrariness. Maybe this is just where we kind of stop explaining. There just is a multiverse of the right kind, no further explanation. I don't find that hugely satisfying. But the last sort of explanation, and this returns us to the kind of creation explanations and what's right or wrong about those, would be a necessitarian explanation. The universe exists because it has to. Why does this exist? Because it's necessary that it is so. Why is 1 + 1 = 2? It couldn't have failed to be. So you can imagine this in a positive way. It's because this fact is necessary that it's true. Or you can imagine it in a more negative way. It's because this fact is necessary, it couldn't have failed to be true. So there's no genuine contrast to be drawn between its being true and its not being true, so there's no genuine kind of target for the explanation. So we're kind of misguided to think that necessary things need explanation at all. That would get you out of explaining a necessary creator, if you think there's some kind of divine entity that necessarily exists and creates. If they're necessary, they don't need explaining. But then the same thing could potentially be said of the universe. It necessarily exists, so it doesn't need explaining. And it's not clear why it's satisfying in the one case and not in the other. Okay. Just want to note that even if the universe necessarily existed, it didn't necessarily turn out the way it did. It could have been that there was necessarily some Big Bang from which different forking histories all spread out. So there's still contingency in what we see, even if necessarily there was something like this. Okay. So lots and lots of different kinds of explanations, probably kind of dizzying number of different kinds and styles of explanation here. The aim is just to kind of get people thinking rather than to kind of close down any of these debates. I don't think there's any impossibility in principle in explaining the Big Bang. We can do that. We can try to do that. We might end up with bad explanations, but I think we can at least try to explain it. We can explain it using more physics, or we can look outside of physics to designers or to metaphysical principles of various kinds to explain it. And we shouldn't write off those non-physical explanations altogether, but we should subject them to the same sort of scrutiny and the same sort of critical standards that we subject physics explanations to. So yeah, time will tell whether any of these strategies actually helps, whether it gives us good explanations. Thank you.
Thank you, Alastair. Any questions? Yes.
Thank you, Professor Wilson. That was really fascinating. I'd just like to ask about what you think about the limitations of the fact that we are minds inhabiting space-time. And you seem quite optimistic that we can answer these questions, but if you look at physics and how sort of our intuition can sometimes mislead us in terms of thinking about relativity and quantum mechanics, because we're just not used to being in those regimes. In a time where time doesn't exist and where space isn't as we know it today, how can we possibly use the logic that has emerged through our experience in a very different realm?
It's really hard because we don't know how far we can trust the different ways of reasoning that we've got. And it might be that when I talk about some of these explanations, grounding explanations, for example, what I'm doing is kind of taking my intuitive understanding of cause and effect and like letting that roam far beyond where it really belongs and kind of ending up kind of getting tangled up. Because if we have, suppose we've evolved cause and effect reasoning to be able to handle the things we engage with, you know, kind of bicycles, lunches, lecture theatres. And then we kind of start thinking about very abstract physics. It's going to be very natural to reach for the tools that we've got and try to apply them, even if they don't really kind of belong on that subject matter. So there's a real risk here. And I think there's a spectrum. I mean, mathematics and logic, I think we probably have kind of better reason to think will successfully extrapolate to new regimes than our thinking about kind of matter and mind do, for example. Because we kind of already know that matter isn't a kind of a universal thing, that there were regions of the big, you know, times in history where there was no matter at all. But like, we think that math still applied there. So like, to the extent that our intuitions are tied up with matter, we should be mistrusting of them. But we do have some ability to identify like logic and math as more universal. How we do that is, and like whether they still ultimately might be not trustworthy is a really interesting question, I think.
Thank you.
Yes, in the corner there. Yes. Sorry.
Hi, thank you so much for your talk. Could you explain more how the heat death of the universe will cause a new Big Bang, or how the cold spread out universe will become a hot dense one?
Yeah. So it's this is a feature of conformal cyclic cosmology, and I mean, I can't do better than Roger Penrose in kind of explaining the ins and outs of it. So I would. He's got several presentations of it, including a Nobel Prize lecture from a few years ago that I'd recommend for the details. I mean, basically speaking, the idea is that you can think of it this way. The Big Bang didn't have any kind of detail and structure to it because nothing had happened yet. So everything was kind of very smooth and homogeneous. Nothing had happened yet to kind of go one way rather than another. And then by the time the universe is spread out to a heat death and, I think that the way to think about it is that the stars will all kind of burn out and all matter will be converted ultimately by spontaneous decay to photons. Space will continue to expand and the photons will continue to spread out in it till all there really is empty space with the vanishingly rare occasional photon in it. A universe like that also has very little structure and detail to it. It's so kind of spread out that it's kind of smoothed itself out. And that smoothness it achieves by spreading out almost completely is mathematically analogous to the smoothness that's there at the Big Bang because kind of nothing has happened to disturb the smoothness yet. I don't think I can necessarily say a lot more. Roger Penrose is your man for explaining this.
Okay, thank you.
Yes, so this gentleman in the red in the middle.
Hi, thank you very much for your talk. I was just going to thinking about the comment that you just made about the smoothness at the beginning and the smoothness at the end. But isn't there a problem with entropy? Because at the beginning of the universe, there's this fundamental difficulty in explaining the extremely low entropy of the universe, whereas at the end, by definition almost, you have a very high entropy. So how do you go from the high entropy at the end of one to the low entropy at the next?
It's as if there's kind of a new entropy quantity that comes into existence associated with the new universe. That's kind of mathematically the same, but like different in value from the old.
Yes.
So in the same sort of way, the new universe kind of comes with its own space-time, where you can trace continuous lines, but there's a transition point where it goes from being very big to very small. And at that transition point, it's not that there's one thing which is simultaneously big and small. There's a thing which is kind of, from the old universe's perspective, big, and from the new universe's perspective, small.
Okay. Yeah, it's quite a trick to pull. Thank you.
It's not my theory. I'm just trying to describe it as best as I understand it.
Yes, the gentleman in the mustard who's had his hand up for a while. Yeah.
Thank you for a wonderful talk. You've made me more curious than ever. Thank you. You spoke about something from something and something from nothing that Krauss talks about. Could that nothing be something we can't explain?
Well, I mean, that's kind of what I think we should kind of say about what Krauss is doing. He's claiming that we've got something from nothing. In fact, we've got something from something, and that something is an explanatory challenge that is kind of harder than the explaining of something that's coming out of it. I mean, nothing has its own kind of peculiarities. It's it's always presented philosophical problems. How do you say that there is nothing without talking about it, and then isn't it a something? That you have those sorts of dilemmas.
Conundrums.
If we're about to, maybe this might be. I mean, so when I am telling my little 4-year-old daughter kind of bedtime stories, she asks where the universe came from, and I made up. They tell her lots of stories about the pixies, and I made up a story where the pixies made the universe, and they. In the story, the pixies didn't exist, but they really, really wanted to. And they wanted to so much, and they wanted to so strongly, that brought the universe into existence. And so there it was something that really wasn't an anything making a something. So there is a question about whether nothing could possibly have the features required to bring something into existence. And it depends what nothing is.
So the gentleman in the white shirt had his hand up first, down the front. Be quick.
Thanks. So for the past Big Bang, you needed a false vacuum for the inflation to happen.
Yep.
So in the conformal theory, is there a second false vacuum? And then if it carries on, is there an infinite amount of false vacuums? So we just keep bouncing into ever deeper false vacuums to carry on like that? Yeah, I think that would be the way to understand it. I mean, the thing about Penrose is that he's not really working in a quantum setting. He's trying to do as much as possible of this with classical general relativity. He's thinking that quantum mechanics will break down in a way which means that some of those the questions about the quantum features of these states won't have to be addressed as directly as we might normally think we do. That's part of why these theories, I think, are not widely accepted, because they don't mesh with a very plausible, widely accepted approach to the quantization of gravity. So, but yeah, in terms of like how specifically this works, how Penrose would answer that, I'm afraid I can't say. Yes. But I think so. I think it would is the answer.
So, a gentleman in the red, just down the front here.
Thank you. In causative and non-causative explanations, you somehow alluded to the issue of creation and God. But the problem is that it makes a presumption in our explanation, and we become biased. And therefore, we are not really dealing with scientific explanation. We are dealing with a biased explanation. Whereas in science, we go for something that is self-explanatory. It didn't come out, although you really kept your distance from God explanation, but I wonder if you could bring some more clarity that in science, we seek self-explanatory and non-biased explanation.
Yeah. Okay, I mean, there's a few things to disentangle there. And the first thing to say is that it would be great if science was not biased, but it really is all over the place in lots of ways. Like, we can think of like science as having like needing and having bias reduction mechanisms that work often quite well. But the idea that like science is totally free from bias, that no bias ever enters into any decisions about what to work on or what to publish or who to fund, that would be utopian. So if science is working well, it is reducing bias. But I actually think that like if philosophy is working well, it is similarly reducing philosophical bias. And like a comparative approach to like different religious accounts of this would also, I think, want to try to look for potential common factors amongst different different religious stories, and identify some of them as highly contingent on the particular cultural context, and others as kind of more universal things that crop up very frequently. So I think that all of these different investigations and explanatory strategies do have their own ways of reducing bias. In terms of being self-explanatory, self-explanatory kind of has a special meaning in the context I was talking about, a thing which is capable of explaining itself. So gods and creators are often supposed to be capable of explaining themselves in a way which gets aside the hard question of, well, where did they come from? Suppose they created the world, but what created them? Well, they don't need creating. They are maybe they're self-creating, or they're the kind of thing that just kind of exists without needing creation. Again, I think there's a hard question as to why, if that property can be possessed by a deity, why it can't be possessed by a physical universe as well. What is it about a physical universe that prevents it from being self-explaining in the way that a deity is self-explaining? It's not obvious what that would be. I mean, maybe there are some ideas could be put forward. But if you mean self-explanatory in the sense of not needing kind of interpretation, I don't think anything, even science, is self-explanatory. I mean, we have philosophers of science, we have philosophers of physics whose main job is interpreting science, but scientists themselves spend a large part of their time interpreting and discussing their results. Like every scientific paper had a discussion section that is drawing some conclusions as well as just presenting the raw data. I can see you're not convinced, but from my point of view, there are not such methodological dissimilarities between these different fields. We're trying to come up with plausible total theories, whether we're doing physics or philosophy or stuff in the intersection.
Thank you very much. We're going to have to stop there. Thank you.